Okay, let's continue. The next topic we want to review is recursion. Well, recursion is definitely a scary topic if you just started coding. And even for the student who has been coding for some time, and recursion is also a concept you don't use every day. Well, if you feel this way, that's perfectly fine. Because when I first started coding, in the first maybe 2 years of doing the coding in my college years, I have never used recursion. Well, of course, I know how to do that if I have to do that. But I was trying my best to avoid using recursion in my first 2 years in college. Okay, well, and my argument is, well, we cannot avoid using recursion in this course. So let's try to see how we can do that. Okay, well, for the recursion, the definition is not so hard. We have been doing the function calls from function A to function B. Well, that's okay. Well, if we are calling function A from the definition of function A, and then we are doing recursion. Okay, well, let's see a very small example. If we have a function definition called endless, and inside we print this is recursive, and then I do a endless function call, and that is we are calling the endless right inside of the definition of itself. So what is going to happen? So after we do this definition, how about we call that only once? And if we call that, and this is what we will see. Well, if you keep on printing, this is recursive. And very soon, you will see the next line. That is recursion arrow, because, well, you are doing the recursion call inside the recursion call inside the recursion call. And eventually, if you're going too deep, Python will force you to stop. And otherwise, well, this recursion will eventually claim all the main memory possible on your machine. Okay, well, this is recursion, and this is the bad recursion because it doesn't really do anything useful. So how do we do good recursion? Well, for a good recursion, we should have at least two components. Number one, that is the base case. The base case or base cases, they define when do we stop this recursion. Well, and then if we are not at the base case or base cases yet, and we will have a recursive steps. And the recursive step or the recursive steps will tells us what to do so that we can get closer to the base cases. And for the recursive steps, there are mainly two different steps or two different styles. Well, number one, we want to reduce the problem size by 1. And number two, we want to do a divide and conquer. So for 99% of the recursions, they are using either one of those two styles as the recursive steps. Okay? And number three, well, the third part is not necessary in all the recursions. In most of the recursions, probably you don't really have that. However, in some of the algorithms, like merge sort, we will use the third step. Well, I usually call that the aftermath of the recursive steps. Okay, well, we will see that in the merge sort. Okay, well, let's start from the one very small example about the recursion. We want to do factorials. And the definition of the factorial is, well, if the current number is a 0, and then n factorial, when n is 0, that is 1. Okay? And for the positive values, n greater than 0, and then n factorial equals 1 multiplied by 2 multiplied by 3, multiplied by n. Okay? So that's the definition of factorial. Okay, and say we want to create a function, factorial. So now let's change it to factorial n. So factorial n is a function definition we are going to do later, but if n is a 0, we are going to have factorial n equals 1. And otherwise, well, if n is a value greater than 0, and then factorial n is 1 multiplied by 2 multiplied by 3, multiplied by n. Okay, well, for the base case, Well, this defines where we stop, and that is usually the smallest possible case that the problem is super easy to solve. And for our case, the factorial 0 is a 1. That is our one and the only one base case. Well, in the next part, that is the important part. And remember, we are doing a recursive step. So we are trying to add the recursion into our definition. That is, if n is a value greater than 0, and then n factorial equals n multiplied by n minus 1 factorial. Okay, so what's the difference? Because for this part, it seems that we are still doing the same thing. But what's the important part? We are breaking the factorial n into two parts. First part, that is n. Well, we have already know the n value. And the second part, that is the factorial n minus 1. So we are reducing the n to two parts. N, we have already known that. And factorial n minus 1, that is a smaller problem than factorial n. So that is one of the important thinking, that is reduce the size of the problem by 1, and we have just done that. Okay, and then well, using this thinking, and here is the definition. The definition is, well, we have a factorial n function definition. If n is smaller or equal to 0, we return a 1, and otherwise we are returning n multiplied by factorial n minus 1. That's it. Okay, well, a lot of times when you're coding recursion, you write the code and you feel, okay, my job is done. Really? Yes, your job has already been done. This is the definition of a factorial function that will return you the factorial n. Okay? So let's see another example. Well, let's say we have a list and then we want to sum all the values together. And let's think about that. What is the smallest possible case that we definitely know how to solve? So if we have a really small list, this small list doesn't really require us to break it into even smaller parts. And what can it be? How about we use this one as example? If the length of the list is a 1, what is that? If the length of a list is a 1 and then we only have one value in the list, and what's the sum? The sum of a one value list is the value itself, right? Okay, we are going to put that into a base case. That is, if the length is 1 and then we are returning the value of the first item because that's the only item in the list. Okay, the next part, how do we do the recursive step? Well, for me, I'm doing this version. This is not the only version, but I'm doing if the list is longer than one item. And then I'm holding the first value and plus the sum of all the remaining of the values. Okay, let me repeat. Well, if the length of the current list is greater than 1, and then I'm using one hand to hold the first value, and then I'm going to use the other hand to get the sum of all the remaining values. And then I'm going to add them together. So that is the first item and plus a recursive call sum list of the rest of the values. And this is a slice from 1 all the way to the end. Okay, and then if I want to sum this part, and this is the process. Well, I want to sum the list of the 4 items, 1, 2, 3, 4, and if I'm using this recursive step, I'm using one hand to hold the A, and then using the other hand to figure out the sum of the rest 3 values, the sum of 2, 3, and 4. And then we have to go to a recursive step. Now we want to figure out what's the sum of the 2, 3, and 4. And again, I'm using one hand to hold the first value, which is 2. And now my job is to figure out the sum of the 3 and 4. Okay, and how do we get the sum of 3 and 4? Again, I'm using one hand to hold the value 3, and then for the rest of them, Okay, luckily there's only one value, right? So on my left hand, I have 3, and then on the other hand, I have 4. So 3 plus 4, I know the sum of the 3 and 4 is 7. So I'm going to return a 7 here, so I have got the sum of the 3 and 4 figured out. So I'm going to do a return to the caller because now I know the sum list of the 3 and 4. And then, well, 3 and 4 is 7, and then 2 plus 7 is 9. That is the sum of the 2, 3, and 4. Okay, well, and then I want to do one further return to the top, and then I will have 10. Okay, well, and here is another example. This is also an algorithm you should have already learned from the data structure. That is the binary search. So for the binary search, the thinking is different. Now we are using a different thinking. That is, we want to do a divide and conquer. Well, say if I have a sorted list, and then I want to do a search and find a specific value. Well, what's the easiest way? The easiest way is I can do a sequential search, right? And say, well, the analogy I want to use is, well, I walk into a classroom and there are a few dozen of the students. I'm looking for a student Bob. So how can I do that? I can visit student 1 and say, hey, are you Bob? Well, if the student says no, and then I go to a second person and say, hey, are you Bob? Well, I can keep on asking this to all the students. And there are 2 possible cases. Number 1, if I ask the 20 students, for example, and then he told me, yes, I'm Bob. And I say, okay, I find Bob. So Bob, come with me. Okay, that's the first case. So I have already found Bob. And the second case is, if I have visited all the students, I ask this question, are you Bob, to all the students in this class, and eventually no one said yes. And what does that mean? This means there's no such student Bob in this classroom, right? So this is the thinking of sequential search. We are visiting all the members one by one in order to find a specific value we are searching for. Well, but for the binary search, well, remember we are starting from a sorted list. Since this list is already sorted, we can be a little bit smarter than that. Well, we have the lower bound, which is the very beginning. We have the upper bound, which is the very end. But now, I want to visit the value at the middle first. If the middle value is exactly the value I'm searching for, and then, ta-da, drop down, right? Well, otherwise, if the middle value is less than the value I'm searching for, what should I do? If the middle value is less than the value I'm searching for, and then the information I have is the value I'm searching for. If it is there, it has to be from the middle to the end. Okay, so I'm only searching from the middle to the end because I'm looking for a larger value than the middle. Okay, the similar thing. If the middle value is even greater than the value I'm looking for, and then I have to search from the beginning to the middle because that is the smaller half. Okay, so that is the thinking of the binary search. And remember, we are using another strategy of the recursion, that is the divide and conquer. We are dividing the problem into 2 small parts, and then we will decide, do we do the search in the larger half, or we are doing the search in the smaller half. So every time we are cutting the problem set into 2 smaller problems, and we only have to solve one of them. Okay, so that is the thinking of the divide and conquer. And for the code, I have the code for you, and well, this code is a little bit tricky because even though we are doing a binary search of a list and a target, and we do have to define another helper function. So for the helper, we have the list, we have the target value, and then we also specify the search upper bound and the search lower bound. Okay, well, and if the lower bound is greater than the upper bound, and then we are going to return a false, saying, okay, we have already touched a invalid search space, so there's no such value we are looking for. And other than that, we have the middle value, and then we want to compare the middle value to the target. And if the target is exactly the middle value, we are returning a true. And otherwise, we decide if we want to search in the higher half or the lower half. So that is the thinking of the binary search. Okay, well, here's an example. If we have a list and then we are searching for 3, and how do we do that? We have the lower bound as 0 and the upper bound as 8. So what's the middle value? The middle index should be 4. And then on the middle index, we have 13. So we are looking for a 3. So, well, that is 3 is lower than the middle value, which is 13. So what does that mean? This means if we do have the value 3, it got be in the lower half, right? So I'm going to cross out the 4 to 8 because, well, this part, well, we don't need to search anymore. And then we want to update the lower, for the upper bound, we update that from 3. So now the search space becomes from index 0 to index 3, and then we want to do another search, and then the new middle value is on index 1, and on the index 1 we have the value 1. However, we are looking for 3. This means, well, we can cross out the index 0 and 1. Now we only have the lower bound to be a 2 and then the upper bound to be a 3. That is our new search range. And then if we want to continue, well, we have to do a floor division. So now the middle index is a 2, and on the middle index 2, we have the value 2. So now we have to do another round of the search. So we cross out the 2, and now we have a search space of only index 3, right? So this is what is going to happen. On the search space of from index 3 to index 3, now we have the index 3 as the middle index, and the middle value on the middle index is 8. So 8 is greater than the 3. So what do? We have to search in an invalid search space now, because now the lower bound is a 3. The upper bound is a 2. That is an invalid search space, and if the search space is invalid, we are going to do a return false. This means there's no such value. Okay, well, here is another example, and consider this as a challenge for you. Well, how do you do a recursion to find the largest number in a list? Well, you have to decide a couple things. What is the base case? Well, how about we do this way? Well, if we have a list, we hold the first element, and then for the remaining n-1 values, we want to find the max. So we hold one value, and then for the remaining n-1 value, we want to find the max, and we want to do a comparison. If the first value is larger than the largest one in the remaining n-1, this one is the largest. Otherwise, this one is the largest. Okay? So, well, this is a hint for you guys, and see, well, I'm gonna leave this problem to you, and you should be able to, number 1, design the algorithm, and number 2, you should be able to code that.